The Perseverance rover is about to gather a rock collection with no equal. On February 18, the rover landed in Mars Jezero Crater to gather rock samples and begin searching for signs of ancient microbial life and visible deltas where water once flowed. The rover is set to fill 38 glass tubes with samples of Mars' surface, then send them to Earth like pebbly postcards, souvenirs to show scientists where it has been. But the samples will need to travel a complicated delivery route to get to their final destination. The mission, called Mars Sample Return, will require 2 more rocket launches from Earth, currently slated for 2026 and 2031, and 1 rocket launch from Mars, which could become the first launch from another planet. If the plan runs smoothly, the mission will provide the first cache of rock samples from another planet, complete with details about when, where and how they were collected. The mission will culminate with the samples crash landing on the mudflats of the Utah Test and Training Range. Scientists on Earth will then be able to scour the samples for details about the red planet's climate, geological history and even subtle signs of life. It's something that the entire Mars exploration community is really excited about and looking forward to, says David Spencer, the Mars Sample Return Campaign Mission Manager at NASA's Jet Propulsion Laboratory. And Perseverance is that critical first step. Perseverance is loaded with scientific equipment to help it hunt for signs of life, like Sherlock, which uses an ultraviolet laser to observe some details of minerals, and Supercar, which can spot organic compounds at a distance. But Sherlock is about the size of a large hardcover book, and Supercar is the size of 2 stacked shoeboxes. To study a rock's age, texture, mineral makeup or the climate that it formed under, scientists need access to equipment that's closer to the size of a microwave or refrigerator. These instruments could not be on a rover, they are too large and too sensitive and too high maintenance, writes Rutgers University planetary scientist Juliana Gross, now the deputy curator of Apollo moon samples at NASA, in an email. But we need to use these instruments if we want to understand how these rocks form. Over 30 years ago, an international panel of scientists wrote a report that first detailed their interest in the Mars Sample Return mission. The scientific community knew then that a quick grab-and-go mission for 1 sample, as has recently been accomplished from asteroids, wouldn't be worthwhile on Mars, given the cost of an interplanetary mission. Last July, NASA and the European Space Agency estimated it would cost about $7 billion. A useful sample return mission from Mars requires grabbing a bunch of samples from many scientifically interesting locations. Rocks and minerals record the conditions of these environments from which they crystallized, says Gross. So, bringing back these samples that span a range in age and crystallized at different times in Mars history, we can start to answer some of these fundamental questions. Perseverance will spend its first Martian year, the equivalent of 687 Earth days, in Jezero Crater compacting half-ounce samples of rock and regolith into some of its glass tubes. Most of the samples will be gathered in pairs. At some point during that first year, Perseverance will drop a cache of samples in Jezero Crater, while keeping the second set of samples on board. If the rover is still in good working order after 1 Martian year, then NASA will have a chance to extend the mission. The rover will roll to the edge of Jezero Crater and gather more samples from both inside the crater and along its ridge, also in pairs. Once the rover fills the last of its sample tubes, it will drop a second cache on Mars' surface, again keeping the second set of samples stowed. When Perseverance puts sample tubes down, it can't pick them back up. The rover will drive away, leaving glass tubes of precious geological samples laying around on the surface of a distant planet. That might sound risky, but NASA has a plan. Once we place them on the surface, we will thoroughly document every tube, and where it's located relative to its surroundings, says Spencer. NASA will use local landmarks for on-the-ground references, as well as orbital measurements, to track the tubes. So we'll know, down to the centimeter level, where every tube is on the surface of Mars. Perseverance is also responsible for scoping out the landing site for the next phase of the sample return mission, the Sample Retrieval Lander. The Sample Retrieval Lander is slated to depart from Earth in 2026, and it will be packing the sample fetch rover, which will be designed and built by the European Space Agency. The 5-foot-long rover will have 4 wheels for speed, solar panels for power and one job: gather Perseverance's samples to send to Earth. The rover will drive to the coordinates of Perseverance's caches and use machine vision and artificial intelligence technologies to recognize and collect the sample tubes on Mars' surface autonomously using a robotic arm, which it can do even if the glass tubes are covered by several years' worth of dust. And if something goes wrong with the fetch rover, Perseverance has its backup samples. The most challenging aspect of Mars sample return is just the long chain of events that all need to be successful, says Spencer. We're trying to build in robustness as much as we can. One aspect of that is the Perseverance rover will be capable of delivering samples directly to the SRL, Sample Retrieval Lander. Once the sample tubes reach the Sample Retrieval Lander, either from Perseverance or the fetch rover, they will be packaged into a soccer ball-sized container called the orbiting sample canister. The canister will not be able to hold all of the samples collected, it can only hold one cache. Glass tubes from the second group, which will include rocks from inside and along the edge of Jezero Crater, will be first in line to leave Mars because they will have a greater variety of samples and therefore a more scientific value, Spencer says. The orbiting sample canister will be loaded into the Sample Retrieval Lander's Mars Ascent Vehicle, which may become the first rocket launched from a planet other than Earth. It will ferry the canister into Mars orbit, where the canister could circle the planet for up to a decade. To finally deliver the samples to Earth, the European Space Agency plans to launch the Earth Return Orbiter mission in 2031. The agency plans to put a satellite in Mars orbit that can intercept the canister and contain it in another layer of protection, in case it's covered in Mars dust. Then the satellite will fly back to Earth with its quarry, transfer the canister to an Earth entry capsule and drop it on Utah's mudflats, where giddy geologists will retrieve it. NASA and the European Space Agency haven't yet decided how they will distribute the Mars samples among the scientific community. When Apollo astronauts brought back samples from the Moon, NASA took proposals from scientists around the world for moon rock-based research projects. Those projects have illuminated the life and death of the Moon's magnetic field, the formation of the Moon and Earth and the history of space weathering over billions of years. Perseverance's primary goal is to search for signs of fossilized life on Mars, but there is a lot to learn about Earth's planetary neighbor no matter the results. The samples could provide insights into Mars history and help scientists predict Earth's distant future. And any information about the Martian environment could help the astronauts who, someday, take humanity's first steps on the Red Planet. Bringing back samples to be analyzed in Earth-based laboratories is crucial for our understanding of planetary processes that have shaped our corner of the universe, Gross says. By bringing back these samples that span a range in age and crystallized at different times in Mars history, we can start to answer some of these fundamental questions that ultimately will help us explore Mars safely in person one day.